Welcome to Lab 4. In this lab, you will learn defense mechanisms against Stack Overflow vulnerability and how to bypass them. We have two learning objectives in this lab. After completing this week's challenges, you will be able to recognize popular defense mechanisms against Stack Overflow vulnerability and describe their fundamental limitations. In this week's tutorial, you will write an exploit against a Crack Me challenge compiled with a very primitive stack protection enable. This is a running example of a Stack Overflow vulnerability that we discussed before. It reads a user's input more than the allocated buffer, which overrides the frame pointer as well as the return address. There are two ways to address this problem. First, we can fundamentally eliminate such a vulnerability either by auditing the source code or by using programming analysis. For example, to fix this vulnerability, we can limit the number of characters that we are accepting in this program. However, such an approach is very specific to the program, so there will be no universal and practical way to achieve them. So the second approach that we'll focus on this week is to mitigate exploitation, meaning that we are going to make such a vulnerability harder to exploit. The most popular and widely deployed solution is called Stack Canary, also known as Stack Cookie or Stack Protection. The idea of Stack Canary is very simple. Detect the modification of important values such as frame pointer or return address by simply putting a known value right before them. When entering a function, it inserts a canary value that we know at the bottom of the current frame. When returning, on the other hand, it checks if the previously inserted canary value is still intact or not. When the input buffer is overflow, the canary value is accordingly overwritten, thereby rendering the comparison false. The origin of the term stack canary is rooted from a safety practice at coal mine. A coal miner brings a bird called canary to detect potential gas leakage in the coal mine. The status of the canary indicates the leakage of gases, like the stack canary indicates the possibility of stack overflow. Although the idea of stack canary is very simple, there are numerous design and implementation choices we can make. First, which canary value should we pick? Is it completely random value a really good choice? And when should we generate such a value? Perhaps every function invocation or simply per execution. Second, when is the right place to check its integrity? Is it enough to check only when returning back from a function call? Lastly, what are we going to do when we detect the modification of the canary value? Simply terminate or report it to the user? It turns out there are security implications involved in each decision that we can make in the stack protection scheme. As the stack canary approximately indicates the occurrence of stack overflow, there are a few fundamental limitations. First, it is vulnerable against information leakage. Once the canary value is leaked, attacker can override the leaked value together with the crafted return address. Second, overflow can still happen against local variable. Sometimes security critical values such as array index or function pointer locate right below the vulnerable buffer. Lastly, the stack canary is effective only against contiguous buffer overflow, not against the arbitrary write. To access the tutorial, you first have to log into the lab server hosting this week's lab challenges, so please find the exact information in separate material. Once you log into the server, you can find README files under the tutorial SSP directory, which describe the detail of each step that you should follow. GCC implements its own stack canary scheme called Stack Smashing Protector, shortly SSP. You can enable this protector with fstack protector as a compilation option. You can adjust the number of functions protected with the stack canary. For example, all apply the canary for all functions, and explicit apply it only for function explicitly specified. If you run make in the tutorial directory, you can get two different versions of Crack Me binary, one with and another without the stack canary. If you diff two binary by using our script, you can check how two binaries are compiled differently. This highlights how a stack canary is inserted at the entry of the function and how we compare the inserted canary value with the known value when returning. More specifically, it first reads the canary at GS14, which is from a thread local storage. Then it inserts the canary from the EAX register to the top of the stack. And finally, clear out the register by XORing EAX registers. Checking the canary is more interesting. It first reads the inserted canary from the top of the stack, which is EBP minus OXC. And it compares the canary that we just read with the original canary value at GS14. If both match, it simply returns. Otherwise, it invokes the stack check fail local function, which ultimately terminates the program. Let's see how both programs behave differently. If you provide a long input to the correct me binary without the stack canary, it simply crashes. However, if you provide the same input to the binary with the stack canary, the program simply stops with a warning that stack smashing is detected. You can further analyze the crashing state by running the same program under the debugger. In summary, you can learn a basic defense scheme against Stack Overflow called Stack Canary. More importantly, you will explore a variety of Stack Canary design and implementation in this week's challenges. After this week's lab, you will be able to describe strengths and weaknesses of various Stack Canary schemes and their fundamental limitations. Happy hacking!